2022, Paper 1. Question 1. A textbook lists the diameter of a hydrogen atom as 1.1 times 10 to the power of 10 meters and the diameter of Earth as 1.3 times 10 to the power of 10 meters. So how are these values expressed in prefixes? So for diameter of hydrogen atom, 1.1 times 10 to the power of minus 10 is equals to 1.1 times 10 to the power of minus 1 nanometer, because we know 1 nanometer is equals to 10 to the power of minus 9 meter. Diameter of Earth is given as 1.3 times 10 to the power of 7, convert it to 1.3 times 10 to the power of minus 2 G. As we know, 1 gigameter is equals to 10 to the power of 9 meters. So answer is A. Question 2. A car is traveling at 10 meters per second due north, 10 meters per second. It reaches a bend and a short time later it travels 10 meters per second due east. So this direction, due east. Which statement must be correct? So it did not change its speed because it's still both at 10 meters per second. Okay, but it changed its velocity. Okay. And it accelerates because velocity and acceleration has direction. It did not change speed, but it changed direction. As we know, the definition of acceleration is rate of change of velocity. Question 3. An object is falling vertically near the Earth's surface. At time t equals to 0, it has a speed of 25 meters per second. Downwards, its air resistance is negligible. What is the speed? V question mark at time t equals to 2.0 seconds. As you know, it falls near the Earth's surface, so G is equals to 10 meters per second, which is also the acceleration. So formula for acceleration, A equals to V minus U over T. We know that acceleration is 10 meters per second is equals to finding V minus U, 25 meters per second over the time of 2.0 seconds. Next. Question 4. A train travels in straight lines and decelerates uniformly as it comes to a station where it stops. So, decelerates uniformly means A is a constant. It comes to a stop, means V, final velocity, equals 0. So as we know, the gradient of a displacement ST graph, displacement time graph, is equals to the velocity. Okay, so we're looking for a gradient that is decreasing to 0. So here, this is actually the gradient, and soon it becomes 0. So Q. We also know that the gradient of a velocity Vt graph equals to the acceleration. So here we're looking for a gradient. Since acceleration is constant, looking for a gradient that is constant. And answer is R. So Q and R. A ball is dropped vertically downwards from a tall bridge. What is the motion of the ball when the air resistance is increasing? And what's the motion of the ball when the air resistance is equals to the weight of the ball? So when the air resistance is equals to the weight of the ball, it's actually at terminal velocity. And we know terminal velocity is uniform. Okay. And as it's flowing through the air, so we can have a quick example. When t equals to 0, it's first dropped. What we only have is the weight. As t equals to 1 second, you start to have a little bit of air resistance. So acceleration is actually starting to decrease. But at t equals to maybe an arbitrary number, 10 seconds, the weight is now equals to the air resistance. So where air resistance is equals to the weight, your F net, resultant force, is 0. Hence your acceleration is 0. Okay, and that is when terminal velocity occurs. Question 6. The water in the container exerts force on the walls of the container. The walls of the container also exerts force on the water. Which of the diagram shows the forces that the wall exerts on the water? So as you know that in this system, it's not going to move. The water doesn't move. The container doesn't move. So actually F net is actually equal to 0. Because it's actually in equilibrium and stationary. So the water actually exerts a force outwards here. So the one in red is actually the forces that the water exerts on the container. And the wall will exert an equal and opposite force on the water. Question 7. An object of mass 20 kg m is falling vertically downwards in the Earth's atmosphere. The air resistance acting on the object is 80 newtons. Give it a capital R. In which direction does the force of air resistance act on object, and what is the acceleration of the object? Okay, so here we know the formula F net is equals to ma. Here is actually weight minus the air resistance. So if I were to draw the free body diagram, show like this, the weight and the air resistance. So we can sub in 20 kg. We're trying to find acceleration A. The weight is actually equals to mg. So mass times gravitational acceleration of Earth, which is 10. So it's 20 times 10 minus r, which is given as 80. And we can find A to be 6.0 meter per second per second. And you know that air resistance should act opposite to the motion, so it's actually acting upwards. Question 8. What is a gravitational field? This is just a definition question, same as if they ask you to define gravitational field. So it's a region where a mass experiences a force due to the gravitational attraction. Question 9. A uniform ruler rests on two supports. Three forces x, y, z acts on the rule. So how are the sizes of the forces related? So first we have translational equilibrium. We know that y is equals to x plus z. That's the first equation. So you know that y is the largest force. These two. Next, we taking y as the pivot. So here, okay, we know that the moments of x is equals to the moments of z. So the distance here, we call it dx, perpendicular distance, for z, dz. You can draw the line of action, x, and line of action of z. So the formula for moments is m is equals to f times perpendicular distance. So now we sub in x times dx equals to z times dz. So left side is equals to right side. Because by principle of moments, the anti-clockwise and clockwise moments should be equal. Since dx is greater than dz, the force of dz must be greater than x. That's the second one. Answer is B. Question 10. The diagram shows a hydraulic press with two pistons. The pressure on piston 1 exerted by the oil is P1. Here, P1. The pressure on piston 2 exerted by the oil is P2. The pressure at point X is P. How do P1, P2 compare with P? So as we know, Pascal's principles states that if pressure is applied to an enclosed liquid, the pressure transmitted is transmitted uniformly to all parts of the liquid. Okay, so which means P1 is equals to P2. And for X, point X, we can actually extend out the line to here. Even at point Y, it will be the same pressure P. So at point X or Y, there is this column of liquid H and the transmitted pressure plus the atmospheric pressure. Okay, so that's why P will definitely be greater than P1 or P2. So it has the pressure of the liquid plus the transmitted pressure. Question 11. Which statement about energy is correct? Okay, so let's use you remember COE, conservation of energy, the total energy of the system before and after. Okay, it's constant. So answer is B. Question 12. A car moves down a hill from P to Q with the engine turned off. There is a constant backward force F on the car in direction as shown. In traveling 50 meters from P to Q, the car loses, so displacement S, loses 100,000 joules of gravitational potential energy, GPE, and gains 20,000 joules of kinetic energy, KE. So we know that the work done by the force or by the friction is actually gravitational potential energy loss, because it was at start, it was on the hill, minus the kinetic energy gain. We know the formula for work done is F times S, displacement, so it's equals to 100,000 minus 20,000. Since S is given to be 50 meters, you get this equation and you can find F. Question 13. A student has a small block of metal and wants to show that it's a magnet. Which test shows that the metal block must be a magnet? To test for magnet, the only test for magnet is repulsion. Okay, so repulsion. Question 14. Thermal energy is supplied continuously to water in a kettle to keep the water boiling. As the water boils, water molecules escape as vapor. The water vapor above the water in the kettle is at boiling point of water. How do the molecules of water in the vapor compare with the molecules in liquid water? Okay, so average KE is actually proportional to temperature. So since the temperature is both at boiling point of water, 100 degrees C, for pure water, okay, so the average KE is the same. However, now the force that they're talking about is the attractive intermolecular forces And because of a change in state, the IPE actually increases. Okay, so the liquid water should have lesser IKE and actually less forces of attraction. Question 15. A cylinder contains gas. The volume of the cylinder is constant. Which change to the mass of the gas and which change to the temperature each results in an increase in pressure. So we will increase P. If we were to use the equation, P ideal gas law, P equals to nRT. If you want to increase pressure, and since the volume is constant, you can, R is the ideal gas constant, so it's constant. You can keep the temperature constant, but increase the number of molecules. Or even you change the mass of the gas, number of molecules, the pressure will increase. Another way, PV equals to nRT. Okay, since you know volume is constant, number of moles constant, ideal gas constant is a constant. To increase pressure, you can increase the temperature. If not, we can look at it in diagrams. So, initially you have 3 gas molecules. If we increase the number of gas molecules, in the same container of the same size, because volume is constant, you realize that the pressure is applying by the gas on the walls of the container actually increases. Similarly, if you increase the temperature in the same container, now the speed of the molecule actually increases. It hits the walls of the container with a greater force. Pressure increases as well. Okay, question 16. A beaker of water is heated at the bottom to form a convection current in water. An explanation of the convection current contains 4 statements. So first is actually the water at the bottom of the container becomes warmer. That's 1. And the water expands. So as it gets warmer, it expands. It becomes less dense. And then the less dense water rises and the cold water comes in to replace it because the cold water is more dense, setting up a convection current. Question 17. A thin sheet of material is shiny and white. So shiny and white is bad emitter and bad absorber of infrared radiation. Okay, it's used to wrap around an athlete who has run a race. And so because it's shiny, it reflects more radiation from the athlete back to himself. He's able to cool down more slowly. Question 18 is not tested. Next. Question 19. The water in the swimming pool has a temperature of 28 degrees C. The hot water in the kettle has a temperature of 80 degrees C, which is much higher than the swimming pool water. Where does the water have a greater total internal energy, and where does the water molecules have a greater average Ke? So internal energy consists of IPE plus IKE. So in the pool, it has more mass of water or water molecules. So definitely it has higher IKE and IPE combined. However, the second one is the greater average Ke. So temperature is actually proportional to the average Ke. And since the kettle has a higher temperature, The kettle is the one that has a higher average KE. So the keyword here is average. Question 20. A 500 watt heater is placed in a boiling liquid P, takes 10 minutes T for 360 grams small m of the liquid to turn into a gas. All the thermal energy supplied by the heater is used to convert the liquid into gas. What is the latent heat of vaporization of the liquid? LV. So we know time, T equals to 10 minutes. We convert it into seconds, 10 times 60 seconds. Mass is equals to 360 grams. Let's change to kg, 0.360 kg. First equation, P equals to E over T, energy over time. We can rewrite as energy equals to PT, which is equals to 500 watts times 10 times 60. The second equation that we're going to use, Q equals to mLV, vaporization. Second equation. As we know, Q is the same as E. So we can actually sub in 500 times 10 times 60 equals, the mass is 0.360 times LV. And we can find what is LV. Next, question 21. Which graph shows the period of the wave and of the wave is related to its frequency? So period here is T, frequency is F. The formula to relate both, T equals to 1 over F. So this is similar to a graph of Y equals to 1 over X graph. B. Question 22. What is a wavefront? A wavefront is a line along all the crests of a wave. Okay, it's not the distance between two consecutive crests, because that is lambda, wavelength. There's no such thing as first wave produced by the source. There's no term for it. And then finally, waves is the transfer of energy without the transfer of matter. Okay, question 23. Which row shows the nature of UV and of ultrasound wave? As you know, UV is EM wave, so it's transverse. Ultrasound is just sound, which is longitudinal. Question 24. The diagram shows a ray of light traveling through a semicircular glass block in the direction shown. Angles P, Q, R, and S are measured in degrees. What is the refractive index of the glass? N question mark. Formula for N equals to sine I over sine R. You must remember that it's more than or equals to 1. So here you have the normal. I always said that it's the ray sticking to the normal. So this is the angle of incident. This is the angle of refraction. I and R. To get I is 90 degrees minus P. To get R is 90 degrees minus Q. So answer is A. Question 25. Which diagram shows a diverging lens refracting two parallel rays of light? So A actually shows a converging lens. D is the one that shows a diverging lens. Question 26. A boy stands at a distance of 85 meters from a large wall, D. He claps his hands once and hears an echo from the wall. He then claps at regular intervals. He increases the clapping until each clap is made just as he hears the echo from the previous clap. The sound wave travels through air at a speed of 340 meters per second, V. Which frequency of clapping does he reach? Question mark. So, the boy looks at this. There's a wall here. The sound will travel. It will turn. It will come back. So, distance 2D is actually equals to 85 times 2 meters. 170 meters. That's how far the ball is from the, how far the sound travels, hits and come back, cause echo. So for echo, the formula is given, V equals to 2D over T. V is 340 meter per second. 2D, 85 times 2 over time T. So this time T is actually the period of one full oscillation. The time that the body claps, the sound hits the wall and it comes back. So T here is just the same as big T, 0.5 seconds. And we know the formula, frequency equals to 1 over period T, which is equals to 2.0 Hertz. Question 27. Which diagram shows the direction of the current I and the direction of electron flow E in the circuit? So we know that if this is a battery, this is a positive, this is a negative side. I is to the right, E is to the left from the negative terminal. Conventional current travels from the positive to the negative terminal. So answer here, I, positive minus, so here is E. Answer is A. Question 28. A 12-volt car battery, V, is connected to a lamp labeled 12 volts V and 24 watts P. The lamp shines at normal brightness for 24 hours T. What is the size of the charge Q that passes through the lamp at this time? So we know the first formula, P equals to VI. And we also use the second formula, Q, the charge that we're trying to find, equals to IT. Okay, remember to change the T from hours to seconds. During a lightning strike, question 29. During a lightning strike, there's a current of 300 K amperes, I, between a charged cloud and the earth for 5.0 milliseconds, T. It releases 450 megajoules of energy, E. What is the potential difference, V, between the cloud and the earth? Okay. So, the equation that we're going to use is Q equals to IT. First equation. And from there, we actually use the next formula, V equals to, potential difference equals to, work done over charge. But here, the work done is actually the energy over charge. Second equation. But before you submit the values, please make sure that I equals to 300 K ampere, convert it to 300 times 10 to the power of 3 ampere. T equals to 5.0 milliseconds, which is equals to 5.0 times 10 to the power of minus 3 seconds. E is equals to 450 megajoules, which equals to 450 times 10 to the power 6 joules. So take note of the units. Question 30. The voltage current readings are obtained for different electrical components. Which readings are for a 3.0 volt V and 0.060 ampere filament lamp? As we know, the filament lamp is a non-ohmic conductor. Okay, so it doesn't completely obeys Ohm's law of R equals to V over I. So you'll see that we'll find something that the resistance is changing or increasing. So you have resistance / ohms. You use the formula I equals to V over I. You calculate that it's 0. For 1.0 divided by 0 by 25 milliampere, you should get 40. So on, you get 44. And you get 50 ohms. We see that this is the one that is R is increasing. And answer is B. Question 31. 4 pieces of wire are made of the same materials. They are connected in between the terminals P and Q in the circuit. Which wire is the largest current? Or current is the largest. So you want largest current, you want to have the smallest resistance. And since you're talking about wires, R equals to rho L over A. For a small r, you want a short wire, but a thick wire. So the diameter or the area, okay, should increase. Question 32. The circuit contains 4 ammeters, A1, A2, A3, and A4. The reading on A1 is 4.0 ampere. So here it's 4.0 ampere. Here is current 1. The reading at A2, label as I2, is 3.0 ampere. So what are the readings on the other two ammeter? You already know that I3 is 4.0 minus 3.0, which is 1.0 ampere. And here at I4, it should go back to 4.0 ampere, because I1 is equals to I2 plus I3. The current splits up. Here, it split up to I2 and I3. Then it merges back to I4. So I1 is 4.0. I4 is also 4.0. Since it's given that I2 is 3.0, I3 must be 1.0. Question 33. The diagram shows two circuits. The voltmeter readings are shown next to the voltmeters. Which row is correct? Circuit 1 is a series circuit. Circuit 2 is a parallel circuit. So look at series 1. This V is actually the EMF. So EMF is equals to, in series, V1 plus V2. Here EMF, V is equals to, for parallel, they are equal. So V3 equals to V4. Question 34. A light-dependent resistor, a LDR, and a thermistor are connected in series with a battery. So a thermistor, we will assume there is a negative temperature coefficient, NTC thermistor. Okay. So in this circuit diagram, this is a LDR, this is the thermistor. So which condition will cause the PD across the thermistor to be the largest? So if you want the largest, means the voltage, the PD for the thermistor is the largest. Okay, you want the resistance of the thermistor to be the largest. And for thermistor to be largest resistance, the temperature must drop, because negative coefficient, resistance will increase. So cold. And also, you also want less voltage output at the LDR. You want the LDR resistance to decrease. And for that to happen, it's under the bright condition. So you can remember the example on the street lamp. When it's very bright, the resistance is low, the street lamp turns off. Question 35. The diagram shows the wiring of a heater in a metal case. the terminal X, Y, Z are connected to the wires from a main plug. Which wire is connected to each terminal? So first, this is a switch. For switch and fuse, it must be connected to the live wire. For the metal case, it's always connected to the earth wire. And then the other one would be the neutral. So, A. Question 36. A beam of charged particles enter a magnetic field and changes direction as shown. So magnetic field B, you're guessing the magnetic field direction. So the only combination that will work is that if the beam particle was a negative particle and the magnetic field was it was out of the page, like this. The dots means out of page, so out of the page. So using Fleming's left hand rule, electrons moving a negative charge particle means your I is in the reverse direction. Your F, father, mother, child, your M is pointing out the page, your current is pointing left to right. Hence, your force is downwards. Answer is B. Question 37. Each of the two parallel wires carry a current I. The currents are in opposite direction. So we already mentioned when the currents are in opposite direction, it should repel. Which diagram shows the magnetic field patterns around the wires and the direction of the force acting on the wires? So first, it knows that it should be repelled. This is opposite direction. And how to find the direction of the magnetic field? We use the right hand grip rule. So in this case, it should be this direction. Current going up, grips. Current going down, this direction, clockwise. Question 38. A bar magnet is inserted into the top end of a solenoid. Inserting the bar magnet induces a current in the solenoid, and the solenoid behaves as an electromagnet. The bar magnet is inserted into the solenoid a second time, the same way round, means the north going downwards, but more quickly, so increase the speed. Which row is correct? The magnetic pole produced at the top of the solenoid as the bar inserted should definitely be a north pole. The south pole at the bottom is to resist the change in the magnetic flux linkage. And this is actually, the direction is due to Lenz's law. The effect on the strength of the magnetic field due to the solenoid inserting the bar more quickly is due to the Faraday's law, the induced EMF, the magnitude of the induced EMF in the solenoid. So when you move more quickly, it becomes stronger. So, question 39, tested. Question 40. A transformer has 500 turns in the primary coil, NP, and 1,500 turns in the secondary coil, NS. The current in the primary coil is 0.60 ampere, so IP. The losses in transformer cause the current in the secondary coil to be about 90% ideal for a transformer. What is the current in the secondary coil, IS? Question mark. So we use the formula IP over IS equals NS over NP. And since it's only 90% efficient, we multiply by 90%. So you submit the values, 0.90 times IP 0.60 over IS equals to NS 1500 over MP 500. Calculate IS to be equals to 0.18 ampere. And this is the end of this paper.